Hi, everybody. So sorry about last week. Just a little heads up, I'm having some storms in this area that sound kind of loud. If I disappear, it might mean I lost my power. I don't lose power here that often, but just in case. So any questions anybody has for things from last week or anything else we've covered? That is seeming like a no. Okay, so let's start talking about some interesting stuff this week. So the main thing I want to focus on this week are types of operations you can perform on collections and sequences, and what type of collections we actually have in Kotlin. We're going to be moving into using the existing functionality of Kotlin rather than writing our own. Although you can write your own to implement a collection or a sequence as you want. So to start with, let's talk about. Let me get a little main class here. Let's talk about having just a list of things that we're going to work with. So we're going to start off saying val x equals list of letter A, something like that. Now what this does is behind the scenes it creates an array list. And it's a Java construct. Depending on the platform that you're on, it may create a different kind of list, but it's creating a list that from that X you can't modify. So it's going to look like a non-modifiable list. Under the covers, because it's an array list, you actually could cast and then modify things, but you really don't want to. So what this does for you is if I said x.add b, that's not going to work. But I could cast that x. So I could say x as array list and then say add b, something kind of like that. Now let's see what this does. And we'll do println x again. Why not? Let's go ahead and run this guy. And oh, I'm sorry. It actually this one when I the list of when it has a single element actually creates a singleton list. I forgot about that behind the scenes. Let's do this. Let's put a B in there so it'll have more than one thing, and we'll add a C. Let's try running that. And Java util arrays array list. Interesting. Things have changed slightly. Let's try actually importing a different array list here. See if that helps me out here. Nope. Okay. So I will pass on that for the moment, but let's see. Arrays that array list. That's interesting. I might have to import arrays first. Huh. That has changed. So anyway, that will not be a problem. But one of the things you might want to do here. Oh, what was the trick for this one? I think if I just said to list on that, that changes the actual type of it. Let me see here what exactly that type is, because this used to be a big problem here. Okay, so the actual class of that is a Java util array list. Huh. Let's take a look at this function for a second here, because now I am interested in what's going on here. So we'll see here that the implementation of list of says if there's elements, call elements as list, and elements is this array. Otherwise, return an empty list. So let's take a look at what elements as list does. Array Java util as list. Whoops. So that's actually going to just have some compiled code. So it's not going to show us a whole lot. I'm going to have to poke around and see what actually is happening now because it's a little different than I'm used to what it was. So it's something I didn't want you to do anyway. I just wanted to show you that the list under the covers actually is a mutable list that you could modify. I was just doing something wrong there. But anyway, we're going to treat this as an immutable list. You can't call functions on it that are directly list functions. And you shouldn't assume what type it is behind the scenes, as I just so amply proved. I assumed it was an array list, but it's not the direct array list that we can modify. So anyway, this gives us a list of 0 or more items, and you can't add to it through the X variable. Now, if you want to add elements to this, the way we do it is actually create a whole new list and append an item to it. So I could say val y equals x plus c, something like that. And when you have a list and add an item to it, it creates a brand new list with that item appended. So when I run this guy, we should see the C was added to it. Works pretty well. And you can do that any number of times, adding items to it. Now, let's say that we want to do a few more interesting things in here. So let's see, what was the thing I was trying to do here? I was just looking at my notes on what I had here. So if I just said val list1 equals list of, like that, notice how it's giving me an error there. The problem is I'm not telling it what types of elements in there. So all it has is this empty type list. And list actually is a generic type. We're going to talk about generics later on in the course. But what you need to do is specify the type of each item that appears inside that list. And we do that by specifying the type in angle brackets there. So this gives us the generic type passed to this list of function so that the list that's returned is going to be a list that takes strings. And that's really all I want you to know about generics for the moment. We're going to talk about how we implement those and all behind the scenes. If you've seen generics in Java, it looks pretty similar at this point, but there's some pretty significant differences later on that we'll see. So this is actually going to create an empty immutable list of strings. So we'll have that to work with. And we can add that to something else. We could say val z equals, let's say y plus list1. And that's perfectly fine. We're now appending a list onto the end of the other list. Since that one's empty, we're not really going to see any change there. It's going to look exactly the same. But let's think about what's happening when we create this new list. It is a shallow copy. Oops. Of X. And what I mean by that is it just copies the pointers to the items. So if you think about this first list that we're creating here, we have these two strings that are created in memory, A and B. And those strings have pointers to them inside this list. All the list is basically a list of pointers to some object. So he's pointing to A, pointing to B. When we say val y equals x plus c, we're taking a copy of all those pointers. So now we have x is pointing at those two guys and y is pointing at those two guys. And this is nice because you don't have a duplicate set of items sitting around. It can be a little problematic if you had some other kind of type. Like let's say I had a class cat. And with my class cat, I will say, actually, let me make it a person. I'm going to make it a data class so that we have our toString and all that fun stuff. And I'm going to say we have a val name. Actually, let's make it a var. And a var age int. So here's a nice little person class. It has two properties, name and age. And they're mutable because of the var there. We can actually set them. So let's create a person. Now we have our person instance there, and let's create another, well, instead of that, let's put them in a list here. Person list is going to be a list of person, and let's make another person inside there. Something kind of like that. So now we have a couple people in a list. If we print that out, I'm going to call that person list 1. we're going to see those people printed out nicely because of our wonderful data class there. So we have person named Scott, age 57, person named Steve, age 10. That's great. If we come in here and create a person list 2, which is where we're going to say, let's take our person list 1 and add in a new person here. And let's say this is going to be Sue, and she's 20. Let's come up there and do that. We'll print out person list 2 just to make sure that it's coming back with what we expect. There we go. So we see that we now have this new list here. We created copies of the pointers to those 2 people. And the way we know those are pointers is if we change one of them, we're going to get into some trouble here. So if I said person list 1, the first person in the list is what I want to actually look at. And if I said name equals Humuhumunukunukuapua'a, that's going to change the name of this person in that object. So what we're doing is we're looking at the pointer from that first item, going to whatever person it pointed to and change its name. So now, if we end up printing person list 1 and 2 there, we should see both of them have that name changed because both lists are pointing to that same person. So this is something to be a little careful about. If you want a deep copy, you're going to have to do something else with this. And what we could do, let's say that I wanted to say val person list 3 equals list of person list 1 sub 0 and then some new person. Let's bring in a new person here, Sue. If we do something like this, we're explicitly grabbing the pointers to these people still. And something, the same type of thing here. And so we're still going to have the same kind of issues. Oh, yes, we have a hand raised. Question. It should. Let's verify it. So what I'm going to do is I'm going to come here and say person list 2. We'll say the second person in there. And let's change his name to, or her name to, was it him or her? Whoever it was, Steve. Let's change Steve's name to Dory. And now we'll reprint them. We should see that both of them have changed to Dory. So let's take a look here. So we'll see now at this point, this is the ones that were printed for the Dory. You notice that both the Steves have changed because they are in fact the same person. So we just have 2 pointers to that same person. Kind of nifty. And this is really important to understand. And this is exactly the way Java works as well. Java lists are exactly the same way. If you want to make a copy of things, you have to do a little extra work. So if we take a look at this one here with person list 3, and then do the same kind of thing, maybe instead of Dory, we say dude. And then we'll print person list 3 again. Note that we're changing the one that person list 2 points to. Because we were just copying the pointers here, we should see dude for the person list 3 stuff. And there we go. So we'll see that dude came out for that person list 3. Now, if we want to copy it, if we want to actually make separate instances, then what we can do is take advantage of the copy function that's defined by our data class. So what this should do is make a copy, pardon me, make a copy of the object with all the same data inside of it. So now if we print out person list 4, and then maybe do something kind of like change a name, person list 2 sub 1, let's say Casper. and then we print person list 4 again, we shouldn't see Casper in that person list 4. We should see them in the person list 2. Let me put a little separator there. And so now we see that in our person list 2, we actually did change Casper, but because we made a separate copy of that object, it didn't change it in our person list 4. But what's going to happen with this Sue that we created there and this Sue that we created up here? Those are completely independent objects. We didn't have a copy of a pointer. We didn't have a copy of the object itself. So if we changed the third item of person list 3, we wouldn't see it in other lists because it's actually just a completely independent object that we're creating here. Now, where it gets really interesting is with this copy. As I believe I covered that in the video from last week, you can tweak some of the properties. So I could say person list, well, actually, let's do the same thing I just did up here. Person list 5. So if I went to person list 1, I could copy it, but maybe I want to change the name or the age. So I could say age equals 0, something like that, which is kind of a silly thing to do. But the copy function is really, really useful this way because really all he does is take whatever parameters you've specified and then set those. And the copy function, now we're not going to see his implementation, but let me show you what copy actually looks like under the covers. If I did a class person 2, let's say, and he's going to have, I'm not going to call it a data class. I'm going to make this just a raw class here. And I have var name string and a var age int. What that copy function looks like is something like this. Fun copy, and he's going to have all the same parameters from our constructor, but what we're going to do is something like this. Whoops. And then inside here, the body of this really is just, well, I can just use an equal here, why not? Something kind of like that. This is basically what that copy function looks like that's being generated. The whole key to this is it just uses, oops, I got one more person coming in. There we go. The whole key to this function is that it's just setting up default parameters for each of the parameters coming in. So if you just say copy without any parameters at all, you're going to get a copy of the object with the exact same data. Looks like they're having a little trouble coming in here, but they'll be okay. And then we just create that person with the data. If you override any of these guys, if you specify either of them when you're calling copy, then that will take the place of the value inside there. So this is basically what the copy function looks like. One more time on that. Sure. So if we had something like a class child, I'm not going to put any parameters in him. I'll just define him like that for now. He might have some data, but what would happen here is if I had var child, and it would then create a same kind of thing here, and then say child equals child. Now, what is the value of this? What kind of value do you think that is for the value of child? I mean, we know what the value of a name is. It's just a string somewhere. The value of age is a string, is an integer somewhere. But what is the actual value of the backing field for that child? That's kind of what it all boils down to here. In Java and in Kotlin, it's a pointer. So when you say var child, you're actually defining a pointer to a child somewhere. You're not actually holding on to a child object. And this is one of the things that in Java can be kind of confusing because unfortunately they use the term reference instead of pointer. And there's several places where they use the word pointer inside the Java specification, but these are actually pointers. And a pointer doesn't have to be a memory address or an indirect memory address. That's people's argument about it sometimes. Um, but what you're doing here is you're actually passing a pointer. And that means that this same child can be pointed to by multiple people. When you do this copy here with the this.child, you're actually copying just the pointer. And that way, if you have two people pointing to that same child, they can both modify it. Let's try that out real quick. Let's create a data class child. I'm going to come down here and actually change that to be child2. Oops. So if we define a data class child up here, and I'm just going to give him a name. Note that this is not how I'd model this in real life, but this is this is just something because you normally have a person referring to another person as a child. But let's keep it as a completely separate class for the moment. So if we define something kind of like this, let's define two people as parents who both have the same child. What is happening? Oh, hey, I just screwed up my person. I'm going to say, let's have a nullable child. So you don't have to have a child. And by default, I'm going to define it as null. So what that's done is that now fixed these errors that I had. Because when I define a person up in here, he just doesn't have a child to start with. But let's define a sidetrack here. Pointers to other objects. So let's define a val child A. And I'll just say Trevor. That's the name of one of my kids. And then I'll say val parent1 equals person Scott, who's 57. And then parent2 is going to be my ex-wife, Nancy. She's also 57. And don't tell her I told you her age. Not like you know who this Nancy is. Wahaha. So now we have these two parents. Notice I haven't specified a child on there. I'm going to go ahead and attach that child to each of these, just like that. And now let's do a little print out here. I'm going to say print parent1 and parent2. And let's see what we end up getting. So see now that parent1, you have person with name and age and a child. Person with name and age and a child. So those two people have name and ages. Just do a little separator before all this stuff. But now let's modify the child just to see that we've actually had we're pointing to the same person. So I'm going to say child A dot name equals, he's going to change his name to Mr. Spock for whatever reason. And then let's print these guys out again just to see that, in fact, it's the same child instance being pointed to in both cases here. So what you're passing in here are pointers to objects. You're not actually making a copy of objects. In a language like C++, you can actually have an object referenced as a variable. And you have to explicitly specify when it's a pointer that you're seeking. In Java and Kotlin, everything's pointers. Okay, any questions so far? It just copies the pointers. That's all you're getting. If you want a deep copy, then you have to do something explicit for it to make that deep copy happen. And in a lot of cases, you really don't want that copy. A lot of cases, you really want to be dealing with the shallow copy. Every once in a while, you want to really, really copy things, and it just becomes a lot harder because you really have to define your own type of copy for that. You can't take advantage of the default copy that's created. Okay, so now back to lists. Let me actually take this guy and put him down here. So this one actually, we had the copies of the lists coming in there. I'm going to get a little doohickey down here. So we're copying the items in the list. If we wanted to do a deep copy in the list, we're going to have to get a little bit smarter about things here, or a little bit more clever about things. And what I'd like to do here is take advantage of an extension function to redefine what we mean by copy. Now, we have to be careful with extension functions because they only apply in the compilation scope that you use it. So if you were defining this in some other file, or some other compilation unit tried to use it, they wouldn't be able to unless you imported the code. So what I'm going to do here is I'm going to say, let's suppose that I have a list. And in this case, I'm going to say it's a list of people. And I want to do a deep copy, which is actually going to make copies of those people along the way. This is going to return a list of, whoops, not strings, a list of people. So let's figure out how we're going to do this. What we need to do now is walk through the initial list, which is the receiver to this function. List of person. And that means that you would call this as person list 5 dot deep copy. Maybe we'd say something kind of like val copied person list. So this is what the call would look like. You would say person list 5 dot the name of this extension function. And that means that this is the object that's receiving this message. That's why we call it a receiver. So the object pointed to by person list 5 is receiving the deep copy message. Now, a long time ago, when people were defining object-oriented programming to start with, we really talked about passing messages, and the function calls were really messages. We were asking these objects to do things. So in this case, we're asking whatever person list 5 is pointing to do a deep copy for us. So the receiver, ooh, I before E except after C, how about that? The receiver is actually a list of people, and we have no parameters. Oops, no, I'm going to say explicit parameters. The receiver becomes an implicit parameter. So you can really think of this function as being deep copy receiver. I'm going to say the word this here. You wouldn't be able to type this by hand, but you'd say basically I'm passing in this as a list of people. So all this is syntactic sugar. Boy, I messed that one up royally. It just creates a function that takes the parameter and treats it like this when you use it inside the function. So inside this function, I could say this.forEach and do something with it. I can just walk through that list. Now, because this is the object that's considered being worked on here, it's optional. You don't have to say this in most contexts here. If you wanted to distinguish between the current object and a local variable, then you might have to say this in several places. So let's think about what we want to do here. In order to do this deep copy, we need to create a new list, copy each of the items into it, and then return. Now we can do that by hand by saying val new list equals mutable list of person, something kind of like that. And then we walk through the list. So we'd say for each new list, add it, so the current person, dot copy. Boom. So we can do something like that, and it makes a deep copy of that person. Now, this is deep just to the level of the person. If the person itself had a deep copy function, we would call that instead. But in this case, what we're doing is we're just making a copy of the person, and any of his pointers, like the person pointer to a child, are still a shallow copy. So just keep that in mind. If we wanted to do a truly deep copy, all of your objects that are possibly involved would have to have some kind of deep copy functionality. And so then we're going to return new list, but take a look at the type that's here. So we have list person as the type of this. If somebody on the outside wanted to, they could cast it to whatever this mutable list created. So we could say as list, or sorry, to list, which will make it a non-mutable list. So you get a little more direction on that. There is a way to wrap this, and I'm trying to remember what it was. I'll have to look that up later, but there's an object you can wrap this in so that the people on the outside can't actually copy it. And I thought it was to immutable or something like that. Or you know what it might be? No, I'm gonna have to look at it. But there was a function, and I'm just blanking on it right now, where you could create a wrapper for this or something like that that would uh, make this so that on the outside it was impossible to cast it. That's what I was trying to show you earlier in the class. But I'm blanking on it. I'll check on that later to do. Check how to make this non-castable to a mutable type. I will check that one later. So this is one way we could make a deep copy. And it's a very explicit way. We're creating that list, we're adding all the items, and then we're returning a new list. But we can actually do this pretty easily using some of the functionality that is baked into Kotlin. There's a whole bunch of functions that are defined on collections. So our deep copy 2 can actually be much, much simpler. We can say this dot map, passing in this guy, whoops, I'm sorry, just like that. So this is where we start thinking more functionally on how we perform things. What we did up here was very iterative, or it was not iterative, it was very imperative. We're setting up a sequence of instructions on how to create a new list and add things to it and make that copy. In this case, we're using functions to do the work for us and letting this feel like a sequence of operations that are being performed on a collection in this case. So we're mapping the existing list to create a new list. And what this map function does is it creates a new list applying the lambda to each element. So it's doing exactly the same thing. And if we took a look at the function beneath the scenes here, that's not going to be super readable there. Yeah, I mean, it's if you look at it, it's really doing the same thing. So if we take a look here, this first parameter is creating a brand new list. So that's that new mutable list that we were creating. But it's also passing in the what to change in each element. And if we take a look at this map2 function, we're going to see that we take that new list that we're creating and we're calling add on it just like I was doing before. So we walk through each item, call add on it, but before we just add the item, we transform it using that function that was passed in. So if we look back at what I had written here, this is just kind of a spelled out way of doing that. I'm explicitly saying create that new list, which was a parameter passing to that map2 function. I'm walking through each of the items and calling add, but applying some kind of a function to it. So down here, the map, this is that transformation function. So it's saying what to do when we're adding each element. So this is a much nicer, flatter way of doing things. And I can even write this a little bit more cleanly by saying equals something like that. Oops, I want to make that deep copy 3. And so now we're using this as an expression. And we can even get rid of the this, because in this case we know that map is the function we're calling on the current object, and just say something like that. So deep copy 3 is just a map function applied, copying each item. So let's actually use that to do some things. I'm going to come in here and take my person list 5. And actually, let's actually just start clean instead of having all this indirection with these different people. And I'm going to say, I don't know, Gonzo, and we'll have Kermit and Rolf. And maybe Gonzo is, I don't know, he strikes me as he's 30 years old. Kermit is like 134. And Rolf is maybe 27. It's 26, 27. So now we have these people. What we're going to do is work with this list by saying person list 5 dot deep copy, and I can call any of these. They're all going to return the exact same type of thing, but let's try deep copy 1 to start with. And we'll say deep copy 1 equals that. And then let's print these guys out. So we'll say println deep copy 1. Let's println person list 5. And I'll put a couple little dividers there so we know where this whole section's starting. And then what we're going to do is print out deep copy 1. And let's try modifying this person now and see what happens. So I'm going to say person list 5 sub. We'll just change the first person's name to Piggy. And then we'll try printing that deep copy out. And if this works, we should still see Gonzo listed when we print out deep copy 1. So let's try running this. So, oops, I didn't print out the person list 5. Let's print out the person list 5 so we can actually see those. So we'll see here that in person list 5, the name actually got changed to Piggy, but because we made a deep copy of that person, it's still Gonzo in our deep copy 1. And we can try the same type of thing with, instead of deep copy 1, let's say deep copy 2 for those. And at this point, person list has Piggy in there. So let's actually do this. Let's say Piggy 1 and Piggy 2. And then we'll do a deep copy 3 to call that other function. They all should do exactly the same thing. And let's try running this. So now what we see here is that each of these last two ones we had, well, now it's propagating kind of interestingly. So we had Gonzo, as we saw inside of our copied list, so he stays the same. And this next one, we had made a copy where it used to be Piggy 1. So we see Piggy 1 in the deep copy, but Piggy 2 in the new version, in the original version. And we're going to see the same kind of thing. So now Piggy 2 is the copy. Wait a second, I think I'm looking at this wrong. So we had, here's I really need to like label these lists when I print them. That would probably help. So let's actually make this so it's a little bit easier to read. Well, we'll just do this. So something like that. And deep copy 1 equals that. And then we'll just make sure that we got the right things here. So that should be deep copy 2. And that should be deep copy 3 now down there. Hopefully that'll make it a little bit easier to read. Oh, I see why I was getting confused, because it was printing out these deep copy 3 before each time. So we'll come up here, and then that's 2, and then we'll come up here. This is, yeah, printing out labels on things actually makes things a little more readable, doesn't it? Okay, so now let's take a look at this and see if that makes some sense. Okay, so we had our original list up there. Our first deep copy, we had Gonzo, and then after the change, he still says Gonzo. Deep copy 2, now he's saying Piggy 1 because we were copying person 5. And then the new change makes it Piggy 2, but deep copy 2 still says Piggy 1. Makes sense. And then similar with deep copy 3, we made a copy from person list 5, so it's now Piggy 2. And then after the change, we have Piggy 3 updated in the person list, but Piggy 2 is again that deep copy. So this is something to keep in mind as far as how deep you go with your copies. The lists just have pointers to things. Okay, any questions so far? Okay, now, if you want, you can have mutable lists, but I advise against this as much as possible. There may be cases for performance where it makes a lot more sense. Like for example, in my Android class, there's a gem matcher game that you have to implement. And in that gem matcher game, there's a function that has to shift a bunch of items down. So, as you're doing your gem matching, you remove all the matches and then you have to shift things down and then add new things. And that shift down would be crazy expensive if we kept creating new copies of the list over and over again. So inside of that body, we create a mutable copy of the current game state, make our mods, and then return it as an immutable copy. And that's something for performance that works really well. Sometimes it's very simple to just create a new list each time. But if you have a lot of things happening, it can be much more effective and much more efficient to use that mutable list. I just advise that if you have a function that does that, keep the mutable part inside the function so that from the outside you have an immutable list coming in, and then what you return is an immutable list. This makes it so much easier to reason about what your program's doing, as well as catch bugs. Mutable objects can be really, really tricky to catch bugs, especially in systems like Jetpack Compose, which you use in Android for user interface development. So, but for mutable lists, we can do something kind of like val mutable list 1 equals mutable list of a, well, let's use numbers, 1, 2, 3, something like that. So with this, we can print that list out, and then we can do things like with it like mutable list 1 dot remove at 0, and that's going to remove the first item and shift all the other items back. So if we print that out, let's go ahead and run it. We'll see that we started with 1, 2, 3, and now we have 2, 3, where 2 is now in the first slot there. You can set items. So let's say set the second item to 10. Something kind of like that. Boom. Works out pretty nicely there. But notice how it has that little squiggles underneath there. This, as we saw last week, is using that overridden function set. We can take advantage of operator overloading there because that applies as an operator. So the same exact thing can be done by saying mutable list 1 sub 1 equals 20. And it's a much more natural syntax for doing this. And when we run this, we'll see that you get the same kind of effect out of it there. Okay, any questions so far? We can also add some stuff. So if I came in here and said mutable list one dot add 45, well, we'll say 42 because that's the number. That's the answer. And then we'll come over in here and boom, we've added a new item at the end of the list. Okay, any questions so far? Okay, so now let's talk a little bit more about how we can chain operations together. So I'm going to take just a normal list. So we'll say val list equals list of, what number list was I up to here? Did I have different lists? Oh, I called it person list, so I can just say list one, good. So we'll say list one equals list of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that. Style-wise, you'll usually have a space after the comma. Oh, I thought I did have we'll call him list 2 then. There we go. Now we can walk through that as we've seen. We can say list2.forEach, and then we'll print out it. Or if we wanted to, we could explicitly name it. And this implicit use of it works for any lambda that takes a single parameter. Or, pardon me, we can explicitly name it. And that's perfectly fine in that case. If we didn't use it, we can use an underscore to specify the parameter, something like this. Now, in this particular case, it would probably be a little cleaner to just not have the parameter at all and just let it be it and just not use it. But if you had multiple parameters and you didn't use one of them for whatever reason, you can put an underscore in there. And that's actually a really nice visual indicator to the reader that you're explicitly, intentionally meaning that you don't want to use that parameter. Because if you had the parameter name in there, somebody might think, well, maybe you copied and pasted something and just forgot to change it. But in a case like this is you explicitly saying, I'm not using that parameter. And you'll see in here, we're definitely not using that parameter. So let's do a little println here, a couple separators. Let's run those, and we should get some pretty obvious results out of this. So you'll see that we're printing out 1 to 10, printing out 1 to 10 again, and then printing out all those A's. So that should be what you expected to have happen out of those. Now, the for each operator here is considered a terminal operator on a chain of things. It doesn't return a list to keep working on. But there are several non-terminal operators that you can use. I should say, functions. There are several non-terminal functions you can use that create a chain. So let's say that we wanted to just print out items that are odd. So we'll only print out odd numbers. What we can do is filter our list to just be odd numbers. So we can start with list 2 and then say dot filter it %0 equal 1. So we're going to use this mod operator for modular arithmetic to check to see if the remainder, hello, whoa, somebody should have stopped me there. That would have been fatal. So we're going to say divide it by 2, and if the remainder is 1, It's an odd number. So what this is going to do is return a new list with just odd numbers. And then we can do our for each and print them out. I'm just going to go ahead and put that on the same line like that. And so now we've created this little chain of operations to affect our data, perform some operations on it, and then print out. So if we do this and I run it, we're just going to see the 1, 3, 5, 7, 9 printed out, the odd numbers that we're dealing with. And this is a super effective way of doing things. It's easy to deal with, easy to understand. It's very readable once you get used to this kind of a syntax. So you're doing steps of operations there. But this creates a brand new list in the middle of there. So that filter operation is creating a new list, copying over the values. Again, the values could be pointers, they could be primitive items, and then returns that list. So we now are using more memory. If you had a really big list, this could be a huge memory hit, as well as by creating all that thing and then having to delete that list later, it becomes a garbage collection issue. Depending on what you're trying to do, is we could use a sequence to skip the list creation. And what this sequence idea does is it creates a little object that walks through the list, returning one item at a time, passing it to each step in the chain. So if I did something like this, we'll take that exact same sequence of things, this chain of operations, and put into here as sequence. I'm going to call him a tour guide to walk through the items and pass each along. So let's think about what this sequence is going to do. The sequence is going to create a little tour guide who's going to walk from item to item and pass that to the next item in the chain. Filter is going to take a look at that item in the chain, and this is a slightly different filter operation now. He doesn't return a new list. I'm going to say passes on the item only if it passes the test. So we take a look at this predicate that's been defined by this lambda. And if that's true, then the filter is going to say, okay, let me run the next thing in this chain of events here. So tour guide, take a look at the first item. 0 is even, right? He would come up with a 0 on this. So I'm not going to continue. I'm going to stop my chain of functions here. And then the tour guide goes to the next element, comes down to filter and says, okay, 1. Hey, that passes the event. Filter is now going to call the next thing in this chain, the for each. And so we'll print that out. Then after that's done, tour guide looks at the next one. He's even, skip it, and so on and so on. And so that is using our memory much more efficiently. There's some times when you really have to create a brand new item, or if all you're doing is a terminal operator, creating a sequence is just extra garbage. But think about if you're performing several operations and it's going to create several lists. I mean, if you did multiple filters and maps, that can get very, very expensive. So in this case, the terminal operator is just performing a function on each of those items that's happening. But what if you wanted to do something in the middle of this chain and still wanted to just pass it on? So I could also to just perform an operation in the middle, we can use a function called onEach. So maybe we have our as sequence there, and maybe I just want to, before we filter, say onEach, let's print unfiltered $it, something like that. And then this one's going to be filtered. Oops, missed a quote there. And so what this is going to do for us is this on each is just an operator in the middle that's going to do something with that. So there's some side effect that we're performing inside the Lambda, and then just pass it on as is. So we'll see for this last one here. Let's get a little like that, and we'll run this guy. And so now we're seeing at the end of this guy, every single one is being printed unfiltered. Whoops. Because we're doing that operation in the middle of the sequence. If we did this as a list instead of a collection or a list instead of a sequence, if we didn't have the as sequence, the on each is just going to pass that same list through. So the on each in the case of a collection doesn't really have any cost to it. It's just going to walk through each of the items in that list and do something with it. You're not creating a new list such as filter would do for a non-sequenced one, a non-sequenced chain here. So this guy can be nice to do things in the middle, just as kind of a, hey, I want to have some kind of side effect to run. If it's in the sequence, we're going to have first one goes to on each, and then goes to filter, then goes to for each. Second one goes to on each, then filter for each. Third one goes to on each, filter for each, and so on. If we're doing a non-sequence, it's just going to say filter returns a whole list. Then we pass the whole list to on each. The Lambda gets called for each element, and then we move on. Now there's a really, really good article that I saw that, make a little note here. So it's a great article on sequence or not. And this one has some great visual representations of what's going on. It can really help clear up when it's a good idea to use sequence versus when it's not a good idea to use sequence. If you have a very small number of items, if you're not talking, thousands of items or something like that, then it's not as big a deal. But just keep in mind, if you have a lot of data, it can be very, very expensive. Now, there's a bunch of other things you can do, like you can sort data and things like that. If you sort, for example, that's going to create a new list, even if you do the as sequence, because there's no other way you can do it, right? If you're getting an item passed to you and you try to sort, you need all the items to know where the item's going to go in. So the sequence is then going to treat that sort as kind of an intermediate operation that converts you into just a normal list and then returns the sequence again after that. So those can be pretty expensive operations in either case. Okay, so let's see what else we're going to do here. Let's say we wanted to do something like list2 dot find, passing in it is less than 4. Let's make it greater then to make it a little more interesting. So we'll say val found equals that, and then we can println found. And I believe we're going to get a 5 out of that one. There we go. So we get a 5 there. So what he's going to do, he's going to walk through each element in the list, testing using this predicate. And once he finds something that matches, he returns it and he doesn't walk anymore. So that's how you can actually check for something inside there. Okay, any questions so far? Okay, now we've talked about for each, but there's a lot of times when inside of here, it would be really nice to know which element we were actually talking about. So we could do something like a list2 for each indexed. And this passes in 2 parameters, the actual index and then the item itself. I'll rename that item. And then in here I can println $index : $item, something like that. And because we have 2 parameters here, obviously we can't use it. You can't default one of them. But this would be a bad example, but if we didn't want to actually work with the item, you could put an underscore. Now, if you didn't want to work with the item, you wouldn't be using this function, obviously. If all you want are the actual indices, you could say get the indices from the list itself, and then do a for each. And now the item coming in here is the index that we can print out. And that'll just print out the indices themselves. Now keep in mind that that indices returns range. Now we run that, we just should see 0 through 9 printed out there. Yep, at the end. There we go. Okay, let's make things a little bit more interesting. Let's say we only want to work with the first 5 elements. So we can use that by using the take operator. Say list2, and then I can say dot take 5. This is only going to work with the first 5 elements. And you can use that for sequences as well. That's perfectly fine. And then do something else with it. I will say returns first 5 elements in a new list. And works with sequences. Now we can also say, let's take the last 2 items out of there. So take last 2. Returns list with only the last 2 elements. Does not work with sequences. The thing with sequences is that the only thing you know is I'm getting an element. You have no idea where it was in the sequence. You have no idea how many items there are in the sequence. So take last just won't work with this. So these 2 operators at this point, we have items that were at indices. So we had the first 5, so that was 0 through 4 are the indices. And so now it's going to be items 3 and 4 are going to be the 2 indices that we had there. So whatever those items were in the list, we should see those ones. Now we can also do drop. Returns new list without the first element. And that's going to work with sequences as well. Because if it keeps track of how many items were being dropped and then just returns them on from there. So in this particular case, should only be the item at index 4. Now this is a horrible, horrible way to get the item at index 4. If you had that list, you could just say list sub 4, right? List 2 sub 4. But I'm just demonstrating what these individual operations are. So if we said val result equals all of that. So the question here, is the result going to be that element 4, or is it going to be a single item list containing that 4? What do you think? Exactly. Drop is always returning a list. Take last, there's a drop last as well. Those are always returning new lists. So if we println result, I believe we're going to see a 5, because I think that list was 1 through 10, right? Yeah, so it's a list containing 5. That was the item at the 4th index. Okay, any questions? Now, let's say you don't know how many items you want to take from the front. Maybe you just have a predicate that you want to test in there. So I could say list2.take while, and maybe it is less than 5, something like that. So this is going to keep grabbing items until it sees an item that doesn't match that, and then it's going to completely stop. And this is something that a lot of times, you can use this to kind of trim down the beginning of the list or the end of the list. depending on items that you basically just want to skip, or drop while. Drop while would be a trim, not take while. Take while it would just get the prefix of something. So that gets however many items from start of list. And of course, we can also have take last while, I believe. Yeah, take last while from the end of the list. And then if we say drop last while and drop while, it strips however many items from the start of the list and strips however many items from the end of the list. These are really super useful functions in general. And sometimes it's useful to reverse a list. So list2 dot reversed. Nice and simple. But there's a subtle difference here. So this one is returns a new list. But if I say as reversed, returns a view of the original list in the opposite order. And that's really simple to write. I mean, this is something that quite often you might use a decorator pattern to wrap a list with something that reverses it. And all it does is when somebody passes an index in, it returns the item at the length of the list minus that index, -1. Make sure I get that right. I think that's right. And so by doing that, it's much, much more efficient. If you just need a list of items, you actually have to have a list that's been reversed, then list.reversed can be really useful there. But in most cases, you probably just want to use as reversed. It's going to be much, much more efficient. Okay, and then I just also want to throw in here list2 dot distinct. Let's actually make a new list here. So I'm going to say val list3 is going to be a list of 1, 2, 3, 1, 2, 3, 4, 5, 3, 4, something like that. So by saying distinct, this is going to create a list that only has unique items. And let's see what that actually looks like when we run that. Oops, list 3. And there we go. It's 1, 2, 3, 4, 5. So as it's adding to the list, it says if the item's already in the list, don't include it. And I believe behind the scenes that actually creates a set and then returns it. But let's see. Yeah, he creates a mutable set and then returns a list. And a mutable set is basically just a hash table behind the scenes. And as it adds things in, if the item has already been seen as a key, it just doesn't add it again. Now, the interesting thing here is it's actually printed out in that order. I believe there's no order guarantee there based on what I'm seeing in the code. So let's get out of there and let's try changing this up a little bit. Because that one we just happened to get, it kind of looked like it looks at each item and then things weren't added to the list. But let's change these up a little bit here. 5, 4, blah, blah, blah. And let's just run that now. That is very interesting. I wonder what it's using. I'm guessing it might be using a tree set. Oh, a linked hash set. So what it's creating there, a linked hash set is actually going to preserve the order for us. So that's actually kind of cool. Interesting. I didn't know it was using a linked hash set on that. It's always fun to try these and then learn something new each day. Normally, I wouldn't have counted on the order of that, but it's actually because it's using that linked hash set, it's going to preserve the order and skip later ones that are duplicates. Interesting. Okay, any questions so far? Okay, so now let's talk about using some classes inside here. Well, it's 8:30, so this is actually a good spot to break for during the class here. So let's say 8:41, we'll start back up again. Okay, we're back. Uh, any questions on anything so far? Okay, so we're going to do things that are a little bit more interesting with some objects instead of just simple lists there, well, list of objects. Um, to do this, I've defined a mammal class, kind of similar to what we did early on, where this is an abstract class, meaning you can't create an instance of it. He has two properties that you can't change. There's no setter on them, so name and age. We have class dog and cat, which extend it, and we're defining primary constructors that don't define any properties and then pass those to the superclass primary constructor. So in this case, it's assigning the name and the age. For human, we do the same thing, but I made him open so that we can actually continue extending him down the line there. So doctor is going to be an extension of human as well there. Now I've created a list of mammals here, some dogs, cats, humans, and doctors. And let's do some stuff with them. Let's say that we only want to take a look at humans in a list. I could say mammals dot filter. What is it? Filter is instance. That's the one I want. Filter is instance human, just like that. And what this does is returns a new list uh, of just humans and subclasses. So that'll give us the human and the doctor here in the list because those are the only two that match that. Is instance is going to check to see for exact matches as well as things that are subclasses. And so then for that, I can say on each of those, let's go ahead and println human $it, something kind of like that. Actually, I'll say $it.name because I don't have a toString printed, toString defined here. I couldn't make this a data class because you can't subclass data classes, unfortunately. And there's some good reasons for that. I don't want to get down to the murky details on that. So this will print out everybody who's a human. Let's go ahead and run this guy. Whoops. Oh, anyone know what the problem is here? Well, I mean, that obviously won't let us do the toString, but um, based on what it looks like I wanted to do on line 25, what did I do wrong? Yeah, I need curly braces here because right now when I say $it, that expression ends at the dot. So it basically the dollar sign is saying take a name, the name ends at the dot. If I wanted the full expression, I have to put that in curly braces. And so now it.name is the thing that's actually going to be printed out here. So silly me. There we go. So we got human Scott, human the doctor. So note that it did pick up that doctor as well. Now, if I wanted to further reduce it, I could say doctor, and then down here, I'll only see it print doctor for the doctor, but I should see it print human for both. So let's run this. So if human Scott, human the doctor, and then the doctor. Ta-da! So that filter is instance is actually very, very nice that way. So let's see. I actually did that's before the mammals. Let's do one more guy up here. I'm just going to copy this over. So I created a little list here. I'll call it name list. Something like that. So I created a little list of string names, and the on each, I'm printing out the items there. Then I'm sorting the list, and then I'm going to print out the items there. Note that also here gives me a list of things. So we'll see that on each. Let me split this up a little bit here. On each, runs the lambda on each item, whereas also runs the lambda on the entire list. So if we wanted to see the entire list at once, this also is actually pretty useful there, versus on each, which returns just one item into that lambda at a time. So depending on what you're trying to do, the on each takes care of the iteration for you. The also doesn't. Okay. The on each down here is printing out each of those items after the sort. So what we should see here, keeping in mind that we're not doing a sequence, we're going to see the entire list. We're going to see each of those items printed out all at once. Then we sort it, and then we print out the sorted items. So let's take a look at that when we run it. There we go. So we have Charlie, Claire, Mary. Whoops. So Scott, Mary, Zach, Charlie, Claire. That's the original order, and that's done with that on each. And then we have Charlie, Claire, Mary, Scott, Zach. So that is the new sorted order. Okay. Now let's say that instead we said as sequence. I'll print out a couple double lines there. Let's actually, oh, a little too much. Do that. And let's run this. And what happened? Huh. So it should be doing some stuff in there. What did I do silly? So I said as sequence on each. That's interesting. Why is it not printing anything? Okay, I'm gonna have to come back and take a look at that because I thought that should print some stuff. So there's gonna be something silly in there. I'll take a look. Just adding the as sequence made it so it doesn't print anything. That's odd to me. So if I did, oh, there's no terminal operator. That's the problem. With a sequence, in order for it to actually do anything, it needs a terminal at the end. So if I said for each here at the end instead of as the on each, I believe that's going to make it work. Yeah, there we go. Interesting. I would have thought that that original, hold on, I've got to kill a phone call that's coming in. There we go. I would have thought that the on each up here would have printed out things as it was going, but for some reason it is not. That's interesting. But it is actually printing out the for each at the end there. So here's that also doing that line, and then here's the okay, it's an order issue. That's interesting. So it's creating our sequence. The on each, you can see that I really don't use sequences very often. But apparently what it's done is doing is it's only actually triggering things when the terminal operator is run there. So when it gets down to the terminal operator, it's already gone through creating the sorted, but then ends up executing the for each up here, which is these guys. And then the for each at the end is printing these. I'm going to see if I can write up a better explanation on this for you. But the reason it didn't do anything to start with is with a sequence, you need to have some kind of a terminal operation. And with an also, that's basically just kind of leaving the sequence dangling, because any of the non-terminal operators are just added as things that the sequence is going to run. Once you get down to the for each, that's actually the one that walks through each of the elements. So I'm gonna have to take a look at this and see if I can write a better explanation for you. But this is one of those cases where sometimes a sequence is not super obvious. Um, I will write up some of that a little later tonight. Okay, so back to our mammals. Let's say that we want to sort our mammals by their names. So what we could do here is say mammals dot sorted by it dot name. With a list up here, we're able to just say sorted because the items in the list are are comparable. And comparable items in Java and in Kotlin are ones that have a compare function that takes another item and then returns either -1, 0, or 1, depending on if this item should be before, has the same value, or after. And if an item itself isn't comparable, the only way we can sort it is to explicitly say sorted by and then define which item is comparable. Now, if instead we had made our mammals comparable, something like this, then what that means, notice how all of these guys have problems. That's because I haven't implemented comparable up here. But I'm going to implement it at this level and let everybody else inherit it. So I'm going to implement this compare to function. And whoops, not string, should be mammal, because we want to compare mammals to each other. And what this function is going to do is take a look at me compared to this other guy and see who should come first. If you've defined this, if your object is comparable, you can just say sorted. You don't have to say explicitly how to do that sort or which field is sorting. In this case, strings are always comparable. That's just part of their definition. So when I said compare by using that string there, then, or sorry, sorted by using that name, that just delegates to the value of name. So in here, all I'm going to do here is say return name compare to other dot name, something like that. Or I can just do that. So this captures the way we want to sort animals inside mammal itself. Whereas sort by explicitly says which field we should sort. Okay, does that make sense so far? If the object is comparable. Okay. Now the other type of thing we can say is sorted with. And this actually passes in an object that defines how to do the sort. So if your sort, first of all, their first level sort, if, let me put a little comment in here. Sorting. If objects in list implement comparable, can use sorted. If objects don't implement comparable, then can use sorted by if just defining if, let's say, if a property is comparable, and that's the only sort key, or can use sorted with to pass an algorithm for determining sort order. And that's called a comparator. So if you define an object called a comparator, you can use sort with to do that. I don't think I want to do an example on that one right now. But you can define a comparator which takes two mammals and determines which ones come before each other. In this case, we're just going to use sorted by. Okay, so let's see. So I had sorted by, and I can do the same kind of thing that we did with the printing. So we can say on each of them, print out the name and the age, and then do a sorted by age and print out the name and the age to see exactly what's coming up there. Whoops. Let's bring him up here. And now let's see what that looks like. So we'll see here's the first list where it's sorting by name, and we'll see how the names and ages work there. Then we're resorting it by age, and we can now see how that turns out a little differently. So if you have properties that you can sort by, you can just go ahead and use sorted by. Otherwise, you're going to have to look at sorted with or make the thing comparable. Okay, questions on that? Okay, now the next thing we're going to do is take a look at breaking a list into chunks. And you don't necessarily have to do this that often, but if we said mammals dot chunked and pass in a number like 3, then when we do our for each, instead of getting individual animals, we get sublists of size specified or smaller. So the last one may or may not have 3 items in it. And so if I println here, we're going to see that, oops, hello. Let's print their names. That's what I get for not, oh, that was the whole list there. So let's do a it.forEach inside there. You know, actually, let's just define a toString on there. So it'll print out nicely. So I'll come in here and I'm going to say toString, and I'm just going to return the name as the string value. Now let's run that. That'll be a little nicer. Oh, I dropped my println. There we go. So let's take a look at that. And so now we see Fido, Puffball the thing, and then Fifi, Scott the doctor, and then the last element, since there's only 7 elements in the list, the last list just have that. So this gives you a way to just break it down into chunks if you need to work with those chunks as a whole. Now instead of chunking, we can do windowing, which is a little bit different. And what you're going to do is specify the size of the window and then how far you want that window to move. So if you think about having a window that can fit 3 elements, and when it starts, it covers the first 3 elements in the list. If we use step of 1, it's just going to move the window 1 element over. So the first time you're going to see elements 0, 1, 2. The next one you're going to see 1, 2, 3. Next one you're going to see 2, 3, 4, and so on. So if we do this, it's going to slide a window across the list. Okay, let's take a look at him. And so now we'll see, let's get our little guy here. And let's run that. And so now we're going to see Fido, Puffball the thing, Fifi, the thing, Fifi, Scott. And you can kind of see how it's just moving that little window across. Okay, so pretty simple stuff there. And let's see. So I had that list of numbers, right? What did I call that? Was list 2? Let's do a couple operations numerically on some lists here. So let's do a println list2.sum. Oops, was it list 2 or was it number list, right? What did I call it? Where is he? Oh, name list. Oh, I don't have a number list there. Okay, let's make a number list. And let me just grab that. So I don't have to type all those guys again. Oh, that was too much stuff there. There we go. And so now we can println number list.sum, for example. And this will work on any list of numbers, whether they're ints or floats or doubles or anything like that. And where are the other ones I wanted to do in here? So average, min of, and max of. Average, min of, and max of. Now min of and max of are going to take lambdas to convert whatever the object is inside of there. So I can say it and it. So I'm just going to take the object itself, gather them all up, find whatever the minimum value is. So if I take a look at these, I should see things that are pretty obvious there. So the 55, the average is 5.5, minimum and maximum. So these are how you can actually work with the list to actually get those out of there. Now we can do something similar with the mammals. So if we wanted to, with our mammals, to find the maximum age of somebody, we can say it.age. And then when we go here, we should see that 999 for the doctor being printed out there. Okay. Any questions so far? Now, if we wanted to get a Boolean value to describe something, so maybe, are there anything in this list where the age is greater than 30? We could do something kind of like this. If we wanted to say, is everything in the list? So does everything in the list have age equals 30? That's the all. And then we can also have the opposite of that, which is none. Does everything not have age 30? And so we can print these guys out. I think we're going to get a true, false, and a false out of that, if I remember what the data was. Yeah, so true, false, and false. So these are predicates you can use just to test the entire list. Some of them may short circuit. So the any, for example, as soon as it finds one, it's going to stop looking at the list. So it's just going to find, when it has the first one, if it can just say, oh, okay, I'm done. I don't need to bother looking at anything. The condition was true. All is going to have to look at the entire list unless it finds something. As soon as it finds one thing that doesn't match that, it knows it's false, right? And none, similar, it's going to stop the first time it finds where that's true. Okay, so let's see, any other ones I want to put in there? La, 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 la. Where was this? Bum, 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 bum. Yeah, I think that'll work. So let's take a look at a little function that can generate a list for us and then use that. So if we define a function here saying generate numbers starting with this list, we're going to generate a list of 3 items. And those 3 items are going to be the list we started with, +1 and +2. So nice, simple little function there. And let's do a few things with this. List of number lists. So this is kind of interesting because we're defining a nested list here. So we're generating these lists 1, 2, 3, 10, 11, 12, 20, 21, 22, 30, 31, and 32. And those are going to be 3 lists inside of another list. And let's print that out just to see what that looks like. So list of number lists. And we will print something here just to divide them. And let's run it. And so we see now this nested list. So the outer list has the brackets, but then there's a nested list inside. The outer list is a set of pointers, sorry, list of pointers to those other lists. So by calling this function, we're creating a new list on the heap for each one. And then by wrapping that inside list of, we're creating a list of pointers to those lists. So you can nest lists however much you want like this. Now, if we want to get a list of just the first item inside each of those lists there. So actually, what was I? I'm taking a look at the code I had from last time, and I'm trying to remember why I wrote this. Um, let's say that instead of having a list that contains a bunch of lists, maybe we just want all the numbers in one single list. We do that by a function called flatten. So if we say println list of numbers dot flatten, what that does is it walks through and all the sublists, it just pulls the items out and drops them into place. So if I look at this, I should see a single list of just 1, 2, 3, 10, 11, 12, 20, 21, 22, and so on. This is an operation that you're going to use very, very frequently if you do any type of recursive work with lists. Because typically with recursive work, if the recursive functions return a list, a lot of times you're going to want to kind of just collect all that data. And this flatten operation is super, super useful for that. So sometimes you're going to generate that list and you want to, flatten them out like that. Now, another thing we can do here, let's say that we have our list of numbers here. Oh, I see what I did. I had a, let's see, we have number list equals list of 1 through 9. Oh, I already got that. So number list.map. And I'm going to generate numbers starting with it. So this one here, this mapped list that we're creating, is going to take that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and for each of those, generate a number list. So it'll be 1, 2, 3, 2, 3, 4, 3, 4, 5, and so on and so on. And now we're going to have a bigger list based on that. So if I do a println of mapped list 1, we should see a list of 10 lists. And so this is exactly what we expected it to be. But what if we want to do both those operations? I can take this and do the map, and then do a flatten. And then if I print this guy out, we'll see that it actually, that chain generated all those sublists and then pulled all the data together. But I can do that a little more simply. By calling flat map. And what flat map does is it's just a combination of generating the map and flattening as it goes. So it takes a look, and if the result in here is a list, it just merges those in to the overall list that's being created. So if I take a look at this last mapped list, it should look the same as the previous one. So we're just doing the map and then the flatten. This is much, much more efficient than doing a map and a flatten, because remember that map is going to create a brand new list containing all of the items, and then flatten is going to create another brand new list to pull all those items out. Flat map is just going to keep track of, here's a list of numbers I want to create. Let me just add all the items that were inside these sublists here. Now, what if we wanted to skip something? There's a couple ways we could skip. Let's say we wanted to skip the number 5 from this whole process. I could say number list dot filter it is not equal to 5. And then I'm going to skip number 5 to go through there. And when I run this, I should see, oops, I printed out the wrong one. I'm like, that's not right. There we go. So I'm going to see that section here that started with 5, 6, 7. So we see the 4, 5, 6, but then we see 6, 7, 8 as the next one. So the 5, 6, 7 we skipped out of that. Now, there's a couple other ways we can do this that might be a little more efficient. And if I came in here and said, there's 5, there's 5, and instead of doing the filter, oh, wait. The flat one I can't do it with. Well, let's say that I wanted to have the original one. I can say map not null. Let's say that I'm doing this where I'm getting all these numbers coming in, these lists of numbers. Maybe I want to have something that looks like this without having the 4, 5, 6. I can say if it is not equal to 5, do the generate that, else null. And this is a way that you can have inside this mapping function skip some elements. And anytime we have a null coming up, the map not null is just going to completely ignore it, and you're not going to get that value back. So if I look at this, this should return the same kind of thing as this nested list without the 5, 6, 7. So we'll see that the 5, 6, 7 was skipped through there. For some reason, I thought there was a flat map non-null, but not. So if you wanted to do this and then have the dot flatten afterwards, that would now give us that entire list without the 5 inside of it. Could have sworn there was a flat map non-null. Interesting. Okay, questions on those? Okay, now the map function is your friend. I hate the name of it, and it's one of those ones that took me a while to figure out what it was doing just because of the name. If you think of it as a transform each element, if you think the word map means transform each element, it's a lot easier to work with. So if we said something like val mammal names equals mammals dot map, we're going to take a mammal in for each one and just return the name. So this map is going to say, convert the mammal list into a list of mammal names by just grabbing the name from each mammal. So all map is doing is looking at each individual element, running this function against it, and creating a new list with the result of those functions. We do the same kind of thing with ages. And those can be, whatever you want them to be. So, now we've broken out pieces of that. This can be really useful in the middle of a sequence where you are getting objects and working with objects. Maybe you called some external service to get something over the network and just want to deal with one field out of something. You can use this approach to break things down more. Let's say we want to have the average mammal age. We can say mammals dot map it dot age. That creates that list there, and then say average. Boom, there we go. And that'll give us the average mammal age. Now, of course, we could have done the same thing by saying, oh, we've already got the mammal ages. Average mammal age equals mammal ages dot average. That would have been just fine. If we want to get the average age of just cats, any thoughts on what we might want to do here? What would be the very first thing we want to do? Yep, exactly. So filter is instance of cat. And then from there, we just do the same kind of thing there. So we're going to map the age. Now, we obviously couldn't do the filter as instance after that map because we've lost the information. We no longer have a mammal that we're looking at. We only have numbers. So that has to come before the map in this particular case. And then we do our average like that. Okay. You can also apply sum of and things like that as well. Now, a thing that's a little, boy, should I use this example or? Well, let's go ahead and use this example. Let's say that what we're trying to do is compute the sum of the ages without using that sum function. There's other places where this is actually more useful, and I'm just blanking on a good example off the top of my head. But let's say that we had alternate age sum. And what we're going to do is we're going to use a function called reduce, which is going to take an accumulator. So it's basically the value that we're keeping track of over time, and then adding each age to it. So we get that value as the result. So for this particular example, I'm going to say the alternative average age sum is going to be, let's take our mammals. Let's convert the mammals into just a list of ages. And then we're going to take that list and figure out a result based on that list. So you're going to see map and reduce used quite frequently together, where map converts a list into some other things, and then reduce looks at all the items and comes up with a single answer for whatever your single answer happens to be. So let's say we have accumulator and the current value. And the answer for this function, what this does, the reduce runs this lambda for each element, and the accumulator is the result of the previous run. So we start off their accumulator at 0, and then each time we run through, we call this function, passing in the previous accumulator value and the current value. So think of this accumulator as just the sum that we're working on here. So inside here, we're just going to say accumulator plus value is the result. And so this is going to apply at each step through the process. You can think of it as kind of like an induction situation where we start off with a 0, we pass in 0 in the first value, return just the first value at that point, pass in that new value and the next value, sum them, pass in that value, the next value, and sum them, and so on. So this is one way that we could use an accumulator here. And accumulator starts at 0. But what if we wanted to set that initial value ourselves explicitly? The alternative there is to use the fold function, where we pass in an explicit accumulator value. So they both really work the same. The only difference here is what is that initial value? And sometimes this is something that you're going to keep track of items with pointers instead of just numbers. Okay, any questions on that? So let's make something a little bit more interesting. Let's say that I want to keep track of a bunch of statistics at once. So what I can do here is create a little data class here that's going to be used to keep track of the min, the max, and the sum of things here. So my minimum, I'm going to start at the maximum value for an integer, so that if it's compared to anything else, it's always going to take the anything else. Maximum is going to start at the minimum value. So again, as it's compared to other things, it's always going to be the other value to start with. And then the sum is going to start at 0. So what I can do here, let me go back to where that was called, is inside this, I can say mammals dot map it dot age dot fold, and we're going to pass in an instance of that stats object. And this stats object is going to be our initial accumulator there. So I'm going to call it stats when it's passed along, and value. And what I'm going to do in this case is I'm always going to return that same object, but I want to update the values as I'm going. Now these are all vars, so I can update it. So what I can do inside here is say stats dot apply. And I didn't talk about the apply function yet. So actually, let me not use that. We'll come back to that later on. I'm going to say stats.max equals max of stats.max and value. We're going to say stats.min is going to be that type of thing. And stats.sum is going to be plus equals the value. So this is updating the value of that stats. And then I'm just going to return stats at the end of that. So each time through, the fold is going to walk passing in the same object because it takes the stats object that I return and passes it for the next one. And then I'm taking the value and I'm just going to do these computations each time and keep returning stats at the end. And at the end, I'm going to get the stats object out of that. So I can println the stats afterwards. And there we go. Boom, boom, boom. Now, if you look at this, this isn't really buying anything over using a for each, because I could have done the same type of thing with a for each with the value and updating these stats. With the fold, it can give me a little bit of a benefit in doing the creation for me. So instead of having to, before the for each, create an instance of it with a variable and then inside of here reference that variable, this is all kept internally inside the fold. And then at the end, the value is returned for me. So the advantage you get out of this is that you don't have an extra item hanging out here that you created to start with. There is, the apply that I started to type in there. When we start talking about the scoping functions like apply, that'll make more sense, but don't worry about it for now. Okay, any questions on that? This is just another way that you might use the fold function. If instead the stats object had vals here, I'd have to keep returning new vals each time on this. So I'd have to create a brand new stats object with the new values being passed in instead of just updating the stats object like this. Okay, so let's see. Let's say that I wanted to find the age of Scott inside my mammals list. So I could start off with mammals.find, and I'm going to look for somebody whose name is Scott. What do you think that find is going to return? What type comes back from that? Any ideas? Guesses are okay. Any might be an option there, but it's a little bit tighter typed than that. What do we know about mammals? Let's go look at the list up here. When we define list of mammals like that, what do you think the type of that list is? Considering that Kotlin is really good at type analysis. Well, if we look at all the types in the list, what is the only common parent type for that? Or the lowest common parent type, I should say. Mammal, exactly. If I had put something like a string in there as well, now what do you think the common type would be? Any, exactly. So it's any is the topmost type in Kotlin. The only commonality we can determine right now is any. But if I remove this, his type analysis says, oh, looking at all these types, the lowest common type is going to be mammal instead of any. But now let's look at this find down here that I started. Oh, I'm way down here, huh? There we go. Now let's look at this find. What do you think find is going to return? Nullable mammal, exactly. And the reason for that is that we have to say something about what happens if we don't find it. And Kotlin loves nullability, and, explicit nullability. And so in this case, if Scott isn't found, it's nullable. Null is returned. If Scott is found, it's going to be a mammal. So the type of that is mammal question mark. Now, because of that, if I want to continue this expression, I need to do one of two things. I need to either use a bang bang saying, hey, compiler, I really know this thing is going to be non-null. And that's a huge bad idea because there might be a case here and there where you really know that's the case and that's the only thing you can do. But it's much, much safer to use the safe nullability operator, the safe access operator, question mark dot. And now, well, not the age. I want to say how old is Scott. If I want to say how old is Scott, I can write this expression. And this expression should return however old I am. How old am I in that list? 55. That's 2 years ago. There we go. That's better. So this should print out 57. Let's go ahead and run that. There we go. Can't believe I'm almost 60. Wow. How time flies. I'm sure I don't sound it, and I'm sure I don't look it. I look all of 39. So this type of expression here lets us find something. If we find it, print the age. But what if we don't find it? What's this going to print if we don't find Scott in there? Let's say that I put Scotty. What do you think the result's going to be? Well, the find we said can return a mammal or a null, right? So if we get a null, we're not going to evaluate this. We're just going to end the expression, right? So what we're left with is just a null at the end. So this is a case where it might be good to bring our friend Elvis into the room here. Elvis has entered the building. So let's say question mark colon. And Elvis will say, if the thing over here is non-null, I'm done with my work. If not, I'm going to return some value. I'm going to say Scotty not found. And so now if I run this, I get a much nicer result out of this. So my expression no longer has null as a possible value. The value of this entire expression is going to be what? What do you think? Any ideas? Let's start with the value on the left side of Elvis. What type is that value on the left side of Elvis? Not quite. Let's actually back up just a little bit here. What's the type of this value here? So the mammal question mark. So it's a nullable mammal. So if I go a little farther here, there's two possible answers here, right? It's either going to be an int or it's going to be a null, which means it's a nullable int. So the type of that is int question mark. So on this side, I have a nullable int. On this side, what's the type of this guy? This is the easy question. That's just a string. So the choice of this expression is either a nullable int or a string. What's the common supertype? Nullable any, exactly. So this one is an any question as that. So there's, the result coming out of this is either going to be a string or a nullable int. So it's, I'm sorry, the result is not going to be nullable any. It's just going to be any. The thing is that we had the nullable int, but if it's null, we're going to have this side go in. So the result we're going to get is either an int or a string. We can't get anything else. There's no way to get a null when Elvis is involved. Unless Elvis said return null, then you'll have that. But that would be kind of silly for Elvis to return null because his whole point for existing is to not return null. So the type of this is any. Make some sense? You get used to it over time. Nullability, the thing that's really great about Kotlin is how nullability is so well defined in the language. And it's not just an annotation value like you might have in Java. Java, it's super nasty nullability in Java. So easy to have null pointer exceptions. Okay, so now let's say that we want to, whoops, well, I'll keep that as Scotty. Well, I'll put a Scott and say Scott not found. So now let's say that we want to do is we want to group the mammals by their name. And so what I want to do is I want to take this list of mammals and create a map that the keys are the names of the mammals and the values are the mammals themselves. But what if there's multiple mammals named the same? What we're really going to end up creating is a map where the key is the name, the value is a list of mammal objects. And we can do that by saying mammals by name equals mammals dot group by it dot name. And then let's print that out just to see what that looks like. And this is a great function. So see here, Fido is a list of the Fido one, Puffball is a list of Puffball, the thing is a list of the thing, and so on. So this one isn't super interesting because it's just single item lists. But if more than one had the same name, like let's say this was Fido instead of Fifi, and now we run this, we're going to see that Fido has two elements in it. So there's two separate mammals in that list there. I'm going to undo that because I don't want that to be my end result. But this is a great little function that helps you associate your data so you can look things up. So if we had this, we had these mammals grouped, I can then say, what is Scott's age by saying mammals by name sub Scott. So I'm going to use the Scott key, question mark dot age or Scott not found. This is much more efficient. Whoops. What did I do? Huh, that's interesting. Oh, because it's a list of things. So we'll take the first element, something like that. So we're saying look up the list of things that we did the group, and then if we actually have a list, get the first item. If we've got a value, so this is actually because the first thing could be null, then grab the age. Otherwise, Scott isn't found. So when I run this, I should see the 57 show up. Yeah, exactly. Okay. Now I could also group mammals by type. By saying mammals dot group by it class. And this is going to use the Kotlin class metadata to associate these things. So the keys are going to be the doctor class, the human class, the cat class, and the dog class. And so then I can print these out. And let's see what we get. So we have class dog. Kotlin reflection is not available. If you don't actually include the Kotlin reflection library, it won't be able to give you the details. It still knows that it's a dog class, but it won't be able to give you some finer grained details that's in the reflection library. And so now we see Fifi, Fido, and Rex are the three dogs. The cats, we see Puffball and the thing. And then humans, we see Scott. Doctor, we see the doctor. Now notice that this grouping here doesn't include subclasses. It's only things that are explicitly with that class. We're using that class as the key, and then any items that had that key are thrown into a group list by that. Any questions? So now, if we wanted to break those up, we could say print mammals by type for each of those types of classes. And that'll just pull those lists out of the map. Or if it had a class that wasn't in there, like if I came in here and said string, that's interesting. Huh, that's very interesting. Let's try person. Oh, okay. So if you take a look at the type here that it's saying mammals by type, it actually uses mammal as the super type. So anything that's not underneath mammal, it knows isn't inside there. So Kotlin's smarter. Kotlin's always smart on its recognition there. It's really nice. Okay, any questions on that? Okay, so let's see. What's the next thing I wanted to cover in here? I need to talk about this. Well, let me just go ahead and copy this over. I just want to watch my time, make sure I hit everything I need to cover here. There we go. So here's just another example that does a couple other things. So we're going to define a person here with a name and age, just like we keep doing over and over and over and over again. And then we can say, create a list of people. And this particular one here, I'm creating a map of, and this is an explicit mapping operation that I'm using here. So I create a list of key and value pairs. The to operator creates a pair. So each of these is creating a pair object. That's what the to does. And notice how that looks. That probably looks kind of wacky, huh? Normally, you'd think of a function as being something paren something else, but the to here is defined as an infix function. If we take a look at his definition, we'll see here it says public infix fun, and then creating the pair of the two objects. So the object that's the receiver, that's the this, and the object that's the other guy, who's the that. And by defining it infix, this lets you use the syntax, the first item space to space the second item, which is pretty cool. I think this is nice. And this is something that if you're defining a domain-specific language, which we'll talk about later in Kotlin, which is basically trying to make things look a little bit less like a programming language and a little bit more like something readable, these look a lot more like a readable declaration of something. And later on, we'll see how we can make this even look more readable instead of having person, paren, Claire, and 25. This is our first little thing we're going to see there with that infix function. That's kind of cool. So we have string as a receiver and then a person as the that for that. So we take this list of pairs, and if you have a list of pairs, you can call toMap on it, and it'll create a map. And from there, I could just say people1 sub Scott to look up that person inside there. Now I can also, let's say that I wanted to, what is going on here? Oh, that was explicit. So in here, what I'm doing is I'm taking a list of people and I'm creating pairs by calling map. So I take the people, I'm applying this function to each person to create a pair, just like I did up here, where I explicitly created the pairs. And then I'm converting that list of pairs to a map. Now there happens to be a nice simple function called associate by that I can use instead of this sequence of things. So if you ever have a key and then the value is just the thing itself, map and then toMap, you can just replace that with associate by. And so what this is going to do is it's going to say each of these objects, the key becomes the name, the value becomes the object itself. Now associate by will only work if the keys are all unique, because it's not going to have a list of things in this. If I come and print this guy out, people3, there's a bunch of other stuff in here. Let's just comment him out for a second. And we'll run this guy. You'll see now inside this map, Scott equals person. It's not a list of people where we had the associate that I did before, or the group by. The group by created a list of things because we're assuming that the keys might be the same. If the keys are unique, you can call associate by, and then it'll create a map, something like this. And that's useful if you know the keys are all going to be unique. Okay, questions on that? So in these guys here, I'm taking that people, and I'm going to say people, I can break down that list, sorry, that map into two chunks, a list of the keys and a list of the values. The actual type for these is actually collection. I believe that one's set. This one's collection. So keys is a set of items because there's no order to it, and values is just a collection. Again, no order, but you can walk through it. So in this one, I can print out well, keys is unique. That's why it's a set. Collection is non-unique. That's why it's both of them you can just walk through, but the keys don't have a guaranteed order. So we can print them out like that. Uh, or one thing you can do if you want to walk through the entire map is you can do a deconstruction on each of the pairs. So when you say people dot for each, this walks through the pairs. You will see, I'm sorry, entries. So map.entry here is a class that has a key and a value inside of it. And map.entry, if we take a look at him, oh shoot, where is he? Oh, how do I find that? Okay, there we go, map.entry. Oops, that's going to be the wrong one. Now I'm remembering how to do a search. You hit shift twice. So non-project items. There, the Kotlin one is what I want to look for. There we go. So map.entry is an interface, and that's not going to help. That's not the one I want to look at. Huh, that's interesting. I was expecting it to be a data class because it has the destructuring declarations, but here obviously we're not seeing the destructuring declarations because what this is doing for us. Oops, where did I go? Yeah, what this is doing for us. This is a destructuring declaration that would call a component 1 and component 2 inside the object. So I'm a little confused why. So it's in Kotlin collection. Let's see if we can find this in here. Probably maps.kt. Doesn't have documentation at that level. Because this thing should be working against a destructuring against an object that has a component 1 and component 2. Oh, you know what it is? I know what's going on. So if we have a class entry that has a val key, let's say it's a string, and a val value, which is another string, I can define extension methods, which is actually what they're doing here. So I can define a fun entry dot component 1 equals key and a component 2, which is value. So if I dug around a little bit, I'd find these two declarations. So by defining this, we're setting it up so that it looks like entry has a component 1 and a component 2. And then that allows me to use that destructuring declaration. So if I said val entry of Scott and teacher, maybe it's just a map of our jobs, I could then say val name, comma, job equals E. And what is he not happy about here? Oh, I didn't put the word operator on those. These have to be defined as operator functions. So what this ended up doing for me is it now defines that I can use entry in a destructuring declaration. And what the destructuring declaration does is it looks at the object on the right-hand side and then calls component 1 to get the first value, component 2 to get the second value, and so on. So we're using this inside this version of our for each statement to say the for each returns entries. Each entry I'm going to break down into a key and a value pair, and then I can use them inside the function like this. Why do I have two of those? And this is kind of the standard way in Kotlin that you'll have to do if you're walking through a map and want to break down key value for each piece. Hopefully that made some sense at the end there. Any questions? In the Kotlin libraries, they define a lot of extension functions kind of like this. And this is a nice one that, yeah, I was a little confused when it was like entries and interface. And I'm like, huh? Should be a data class, but no, it's like you can just define component functions on top and this works. And you can do this for, things that come from other libraries. It's really nice. Okay, so the rest of this, there's a couple other things here. They have a get or default and a get or else are a couple different functions. So get or default lets you explicitly pass in a default object for if Scott isn't found. Get or else says if it's not found, run this lambda to create the object. Now, what's the difference between those two? Why would you choose one over the other? Any ideas? Notice how in get or default, you have to have created that object and pass it in as a parameter. And if that object that you're returning as a default is expensive to create, that's a big waste of resources. This second one here only creates the object if the thing wasn't found. So you're going to see this kind of pattern used where you pass in a lambda to do something only if a certain condition is applied, because it might be expensive to create that. A really good example of this is that check function that we looked at. So if I said check, let's say dummy person not equal to null, this is probably going to give me squiggles. Yeah. And then some message. What this is going to do is if this value comes back as false, it's going to run this expression here, run this lambda to create a message and then create an exception. And creating an exception is very expensive. So you don't want to do that every single time. But it's, and whatever's happening here to create this message might also be expensive. So we want to only run that if the value is false. Okay. So then this one here, I'm explicitly creating a map, and this is a map class that I defined down here, I think. And this particular map, I'm setting it up so that he holds on to a private default value. And what I've done is I've extended the normal map to say I'm going to implement the map using mutable map. So this by here is what's called a delegation. So this is saying that this class is going to extend map as implemented by mutable map. So this mutable map creates the basic map for us. And then what I'm doing, I'm overriding the get function on the map to say if the get doesn't return anything, return the default value automatically. This is kind of a neat little way to deal with that default value kind of automatically and not have to do any special get or default or get or else. So here, notice how I can say my map dot age. I don't have to have a question mark dot on that because I know it's always returning a non-null. That's what this get does here. It says I'm returning a non-null value coming in. Okay, and I think that's it for this one. What is the next one here? Oh man, I didn't hit nearly as much as I wanted to today. Do I need that for the assignment? Let me check something real quick here. I just want to make sure if I want to use this assignment, I don't have to take too much out of here. I don't think I need to cover that, so that's good. Let's take a look at the next thing. I definitely have to talk about this, and I have 10 minutes. Um, that I don't think I need to talk about. That's yeah. So let's talk about sealed interfaces and sealed classes. The basic idea with a sealed interface and a sealed class, and I'm just going to copy this stuff over instead of typing it this time. What we want to do here is if you have a hierarchy that you want to restrict to just a certain number of subclasses and nobody else can ever extend it, we can define something called a sealed class or a sealed interface. And they're very similar to each other. What it does is anytime you say sealed, the only subtypes of this have to be defined inside the same module that we're compiling. Now, when you're compiling a project using Gradle, you can define other modules. Like if I came in here and said new module and let's see, Kotlin, Gradle, Kotlin, that all looks good here. Maybe I'll call it lib. This module is a group of things that are compiled together. The normal outside top level module here is also a group of things that are compiled together. So these pieces being compiled together versus what's compiled in lib are completely independent from each other when you compile them. You can depend on the other module. Like on the outside here, I can say I depend on this library. I'm not going to show you how to do that right now. But you'd put it in this dependencies block, by the way. You can depend on other modules, but uh, you aren't compiled with them. So the subtypes of a sealed interface or a sealed class have to be defined within the same module. So you think of it as you're defining a library that has a fixed set of types. You can have your own inheritance, but nobody outside can inherit. Very, very nice situation there. So what I'm defining inside here are some classes loaded in error to represent a response from a function. So sometimes you might have a function that, if something goes wrong, you throw an exception to say something went wrong. Or if something went wrong, maybe you return a null. Maybe it's not found. Using a system like this with a response interface really defines a much more concrete reason for an error and lets you have multiple types of states coming back out of a function. So in this particular case, this would be defined for a function that maybe is going off and running a web service to return some data. And during that, there's going to be several types of states coming back. So we might have a loading state and a timed out state, a loaded state, meaning everything's okay, or an error state saying something went wrong. So look at these two first. Both of these extend response, and this one is actually returning the value. This guy returns information about a problem, if we have a problem. These two guys don't have any data. So I'm only going to be returning the fact that it's loading or it's timed out. Because there's no data, I could have defined these as classes and then just created a new instance every time. But because there's no data, there's really no use in creating different instances of it. What we're creating here is something called a singleton. There's only one instance of this class sitting around, one instance of loading. And we can reuse that over and over because the data doesn't change and because there's nothing mutable inside of it. We do that by declaring it an object in Kotlin. And declaring it an object in Kotlin gives you just this class as a singleton instance. Now, what it's complaining about here is it's saying that, hey, you can make this a data object. And what a data object does is it gives you the same type of functionality, the toString and the equals and the hash code and things like that, that you get from a data class, but there's only ever a single instance of this guy. So using these, I can define a function that's going to use that response. And so what this get name from web service function is doing for us, and what I'm doing inside here, I'm assuming that this get value is actually going and doing the work for me. So waving my hands big time, we're not actually defining a web service here, but pretend that the get value call there was the actual work of going out to the web service. Wow, I typed that without any errors. That doesn't happen often. So we're just going to pretend that that's happening. So what we're doing inside here is this guy is taking a function to call to tell us the state. So what's going to happen here is the caller is going to call passing in this function, and at various points we're going to call that to tell him what the current state is. You can see inside here, we first of all say loading. Then, if everything went fine, we say loaded. If everything didn't go fine, we say on, pass an error in there. So this on response call function is being called for different statuses coming out of here. Um, Now, if all you cared about is having this function be synchronous, so this function right now, by the way, is asynchronous, and the yeah, it says whoops, it says most likely start a thread here, or better yet, launch a coroutine to make this guy asynchronous. If we wanted a synchronous one, we would just have him return that response value, and then the caller would wait. In this case, the caller makes this call. This guy starts off a thread to do all this stuff, or a coroutine to do this stuff, and then immediately returns. The caller will then get these calls to on response from that thread to just tell the current state as we're going through there. So this is a way to give us some information in the form of an object that basically has multiple subtypes with different values. So it can be a very, very nice way to handle this. So here's an example of what this might look like. We call getName from web service, passing in some ID. And then here's that lambda that's going to be called at those several spots. So it'll be called for loading. And in this case, we're going to put up some kind of progress meter on the screen. If it timed out, assuming that there was some timeout inside here, we would stop the progress meter and put up a message. If it got loaded, we'd stop the progress meter and then do whatever we need to do with the loaded data. And if there was an error, we'd stop the progress meter and then put up the error message. So this is a way to handle a result coming from a function in a much nicer way than depending on nulls to mean something. Okay, any questions of that? Okay, I got a couple minutes. I want to double check that assignment description again here real quick. Sorry about the delay here. Okay, actually, I think that's in good shape. I'm not seeing anything here that sounds like it's going to be a problem if I don't cover these other things. I guess I've got a minute, so let me mention the null object. Because one of the things we have is when you're doing these different chained calls, if you return nulls, then you have to have that null operator in there. Sometimes what's nice is if instead of returning nulls, you return an object value that represents null. So what we could do here, for example, is if we defined our person class, I might define an instance here that is just going to represent a person who's considered to be null. So there's just no data inside of him. So for example, this lookup person function, instead of now returning a nullable person, he always returns a non-null person. If there's a problem, we return this special instance that represents a non-existent person. So in a case like this, now for this empty list here, very useful null object, what was I saying in that? Oh, an empty list is actually a very nice representation of I don't have any data. So let me turn that off there. An empty list is actually a nice representation of, hey, I don't have any data. So if you're going off and saying, give me all the people, you get an empty list, that's a good way of representing it as opposed to returning a null to say there's nothing left. So in this case here, if we're looking up people with a certain name, we don't make this a nullable list. We just return an empty list. In this type of case, that actually semantically makes a lot of sense. So inside here, maybe what I say is, when the person that I'm looking at is lookup person Scott, which could return null person, I then check, is the value actually null person? If so, report person not found. Otherwise, we'll do something with that person that was found. If we're doing it from a list point of view, we'll look up the people named, and if you do a .for each on that, it won't do anything if it's an empty list. So you don't actually walk through the list there. Or you could be, a little more explicit here, saying, val people, look up the name. If it equals empty person list, do something specific that says there's no people. This guy here, if you want to kind of convert back from a null object into a real null, take if is very, very useful. So we're going to look up people named Scott, and if it is not equal to empty person list, take if just passes that forward as a non-null. If, however, it is null, then we can, if it actually is the empty person list, take if returns a null. And we'll talk more about these let functions and things like that, I think, next week. So don't worry about that too much. But all it's saying is that if the value is not null, do the stuff that's inside this block here. So in this case, the take if converts from the null object to an actual null, so we can take advantage of this question mark dot let. We'll see more of that later. Any questions on anything from this week? Okay, well, I will look over the assignment again just to make sure that everything is in there, that we've covered everything that we actually need, and then post that, and I will see you all next week.